also reorder operations. So this is an example of a store load reordering, in which case the store of flag equal to 1 can happen after the read of tasks. Now, the store load reordering is something x86 is allowed to do. Cardinal rule about how they can reorder things is sequential consistency for single-threaded programs. So they can change the order of memory operations as visible to a single-threaded program. Now, the compiler has additional rules for what it can and can't do, but this comes down to the specific compiler implementation. And this is encompassed in the language memory model. So, for example, Go and C++, and I think Java too, guarantee that if you use locks and other synchronization mechanisms correctly to make your programs data erase-free, then they will give you sequential consistency in multi-threaded. Guarantee that memory order is preserved. Now these instructions are called memory barriers or memory fences. Again, in x86, examples are mfence, which is a complete memory barrier. So loads and stores are not reordered when you use an mfence. You have a store fence called sfence and a load fence. Is the lock instruction prefix. The lock instruction prefix is a prefix that you can apply to memory operations like adds and increments, and it gives us both. It makes the instruction atomic, and it's a full memory barrier. That sounds useful. Can we use the lock prefix to solve our conundrum? Why, yes, we can. The lock prefix compare and exchange, or compare and swap instruction, is also called an atomic compare and swap. This gives us exactly what we need. What this does is it conditionally updates a variable. So it checks to see if the variable has the expected value, and only if it has the expected value, it updates it to the desired value. How are we going to use the atomic compare and swap? Well, let's see. So here's a program. Now here the first thing we do is we're going to do that atomic compare and swap. So only if flag was 0, it gets updated to 1, and this happens atomically. We do our thing, we read or write, and then when we're done, we atomically store flag back to 0. Now if the compare and swap fails, it means implementation is a simple spinlock implementation, and these spinlocks are used all over the place in the Linux kernel. The other thing to note is these atomic compare and swaps are the quintessence of any lock implementation, as we'll see throughout this talk. Okay, so what is this atomic compare and swap going to cost us? Right, that's what we care about. Well, let's just measure it. Here's a simple micro benchmark. So what we do is, in a loop 10 million times, we atomically store, so this is in C, so we atomically store an integer and measure how long that operation takes us. We see that with a single thread, it takes about 13 nanoseconds, and when we have multiple threads trying to do this, they're all effectively serialized. Those are the guarantees, that's the special guarantees this operation gets us. So we see they're effectively serialized, and it takes about 12 times as much with 12 threads on my 12-core machine. Cool. So this is pretty nice. We have the scheme, it gets us mutual exclusion and atomicity and memory ordering guarantees. But there's one problem, right? We have this thread just spinning, just burning CPU cycles and not doing any useful work, which is wasteful because we could run other threads instead on the CPU in this time. You know what would be really nice? It would be really nice if we could, if the thread tried to do this compare and swap, and when it failed, instead of spinning, if we could just put it to sleep. Put it to sleep until we could put it back, until it could get flag again, right? That sounds pretty nice. Well, luckily for us, the Linux operating system gives us a way to do this. Linux has these futexes, and futexes are both an interface and a mechanism to sleep and wake threads. So they give us a way for our program to request to sleep and wake up threads.
Yes.